Hi, welcome back to the class. So now we are going to go into a bigger topics talking about dangerous properties of engineering materials. And these topics itself cover several chapters from chapter 6, chapter 7, and chapter 8 in the textbook. And this will takes about 3 to 4 weeks to finish the material. So bear with me and have fun. So first we're going to talk about chapter 6, which talks about fire and explosion. Chemical presence of substantial hazard in the form of fire and explosions. The combustions of 1 gallon of taurine can easily destroy an ordinary chemistry lab in minutes, and people present may be killed. So the potential sequence of fires and explosions in pilot plants and plants environment are even greater. So the 3 most common chemical plant accidents are fire, explosions, and toxic release. So we have talked about this in the past. And the organic solvents are the most common source of fires and explosions in the chemical industry. Chemical and hydrocarbon plant losses resulting from fires and explosions are substantial, with yearly property loss in the United States estimates at around 300 million. Additional losses in life and business interruptions are also substantial. So in order for us to prevent accidents resulting from fire and explosions, we as the engineer must be familiar with fire and explosions of the properties of the material, the natures of the fires and explosions process, and the procedures to reduce fire and explosion hazard. There are 3 essential elements for combustions, which are fuels, oxidizers, and ignition source, as you can see in these slides here. Fire, or what we call burning, is a rapid exothermic oxidation of an ignited fuel. The fuel can be in solid, liquid, or vapor form, but vapor and liquid fuels are easiest to ignite. The combustion always happens in the vapor phase. Liquids are volatile and solids are decomposed into vapor before the combustion. When fuel, oxidizers, and an ignition source are present at the necessary levels, burning will happen. This means that the fire will not happen when the fuel is not present or is not present in sufficient quantities, or an oxidizer is not present or is not present in the enough quantities, or that the ignition source is not energetic enough to initiate the fire. This slide lists the common sources of the various fuels, oxidizers, and ignition sources in terms of solid, liquids, and gaseous phase. The biggest differences between fire and explosion is the rate of energy release. Fire release energy slowly, whereas explosions release energy rapidly, typically on the order of microseconds. Fire can also result from explosions, and explosions can result from fires. A good example of how the energy release rate affects the consequences of an accident is the standard automobile tire. The compressed air within the tire contains energy. If the energy is released slowly through the nozzle, the tire is harmlessly deflated. But if the tire ruptures suddenly and all the energies within the compressed tire released rapidly, the result is a dangerous explosion. The next 2 slides talk about the commonly used definitions that related to fire and explosion. So the definitions are discussed in greater details in the later sections together with other online video. The next video shows a chemical reactions explosions that happens in 2007, where a runaway chemical reactions during the productions of a gasoline additive that destroys a lab in Florida, killing 4 people and injures 32. The blast, which is equivalent to about 1,400 pounds of TNT, damaged buildings and injured office workers hundreds of feet away.
On December 19, 2007, a powerful explosion and fire occurred at T2 Laboratories, a small chemical producer in Jacksonville, Florida. The blast killed and injured workers, destroyed T2 Laboratories, and extensively damaged 4 nearby businesses. Windows blew into offices, striking workers with flying glass.
The explosion at T2 Laboratories is one of several accidents that the CSB has investigated caused by runaway chemical reactions. Accidents resulting from reactive hazards occur too frequently and often have serious consequences.
Behind me on this concrete pad, there used to stand a structure some 50 feet high that had a reactor vessel in it, in which the company that operated here, T2 Laboratories Incorporated, manufactured a chemical known as methylcyclopentadienyl manganese tricarbonyl, or MCMT for short. The entire structure and reactor vessel were blown away in the explosion.
T2 produced MCMT, a gasoline additive, in batches using a 2,500-gallon reactor. An operator controlled the process with a computerized system in a nearby control room. In the first step, liquid chemicals and sodium metal were loaded into the reactor, heated, and then mixed with an agitator. The reaction produced hydrogen, which was vented to the atmosphere. In normal operations, when the temperature reached 300 degrees Fahrenheit, the operator would turn off the heating system. But because this reaction was exothermic, or heat-producing, the temperature inside the reactor would continue to rise. At 360 degrees, operators would begin to periodically fill the reactor's cooling jacket with water. As the water boiled, heat was removed, controlling the temperature. However, on the day of the accident, the CSB found that the operator tried to cool the reactor as usual, but the cooling system likely malfunctioned, perhaps due to a blockage in the water supply piping or a valve failure. The temperature and pressure inside the reactor began to rise uncontrollably in a runaway chemical reaction. T2's co-owners returned to the plant after a worker called to report the cooling problem. While one owner searched for the plant mechanic, the other went to the control room. Concerned about a possible fire, he warned employees to move away from the reactor. Inside the reactor, the pressure was still increasing, reaching 400 pounds per square inch and bursting the rupture disk. Witnesses heard a sound like a jet engine as high-pressure gas began to vent from the reactor. But it was too late. Within 10 seconds, there was a massive explosion, equivalent to about 1,400 pounds of TNT. The blast damaged buildings over 1,500 feet away. Debris rocketed up to a mile. The co-owner and the operator in the control room were killed. 2 operators further away died from flying debris. 32 other people were injured, including 28 at nearby businesses.
This facility housed multiple types of chemicals. That was a kind of a mass storage of everything you can think of, and it was all mixed together and it was all burning together. And for our perspective from the hazardous material side, it makes kind of a worst-case scenario.
Damage from the explosion was so severe, 4 nearby buildings were condemned.
My office personnel heard a whistling sound in the area, and as they looked out the window, they saw an orange glow, which was the blast coming off of the explosion, and it came to our offices and it blew in all the windows in our office trailers. Immediately, it was a shock or a surprise, and then all of us were shaking afterward.
In 2002, the CSB completed a study on reactive chemical hazards. The study identified 167 serious accidents involving uncontrolled chemical reactions between 1980 and 2001, causing 108 deaths and hundreds of millions of dollars in property damage.
When mixing chemicals that have an exothermic reaction, you need to be aware of the amount of energy that could be released by the reaction to prevent vessels from bursting like the one that happened here.
T2 developed its MCMT process using a 1-liter reactor. The company then scaled up the process directly to full production volume in the 2,500-gallon reactor. After 41 batches, T2 increased the batch size further by 1/3. As the scale of the reaction increased, effective cooling became ever more difficult. During 175 production runs making MCMT, T2 periodically experienced problems, such as unexpected temperature increases, but the company never fully investigated the causes. And T2 had only equipped the reactor with a simple cooling system using city water. When the system malfunctioned, there was no backup cooling immediately available to control the reaction.
The most important thing to managing reactive chemistry hazards is that you have to have a thorough and complete understanding of your chemistry under design conditions and also under all foreseeable abnormal conditions.
The CSB has noted that to prevent reactive chemical accidents, companies should identify and thoroughly evaluate reactive hazards in their processes, implement appropriate emergency pressure relief systems and other design safeguards, develop effective operating procedures and training programs, and carefully manage any changes to existing processes, and plan for possible accidents, including evacuation drills and emergency response exercises. Although T2's owners had undergraduate degrees in chemistry and chemical engineering and experience in the chemical industry, neither had been trained on how to recognize or control reactive hazards.
A large portion of the incidents have occurred because the people who are actually running the process were not aware either of the existence of the reactive chemistry hazard or of the potential magnitude of the consequences associated with that chemical reaction hazard. So a lot of the problem, I think, is education and awareness.
The board noted that multiple sources of information are available on how to control reactive hazards, including publications from the Center for Chemical Process Safety, the Design Institute for Emergency Relief Systems, and the UK Health and Safety Executive. Following the T2 investigation, the CSB recommended that the American Institute of Chemical Engineers work to incorporate education about reactive hazards into college-level chemical engineering curricula.
Reactive chemical hazards continue to be a too frequent cause of chemical accidents. Improved industry practices and increased education will help prevent these tragedies. Thank you for watching this CSB safety video.
The next video or the next case studies talk about dust explosions that happens at Imperial Sugar Plant in 2008. So total 14 workers was being killed in a series of these sugar dust explosions at the Imperial Sugar Plant near Georgia. So these videos explain how the accidents occurred.
At 7:15 p.m. on February 7, 2008, a series of violent sugar dust explosions devastated the Imperial Sugar Refinery in Port Wentworth, Georgia, just outside Savannah. Explosions raced through the buildings, fueled by accumulations of combustible sugar dust and sugar that had spilled from equipment. Thick concrete floors heaved up, and brick walls were blown into stairwells and work areas, blocking many exit routes. Fires spread rapidly. 8 workers died at the scene. 6 more died later at a regional burn center. Dozens of others were injured. The plant's massive sugar-packing buildings were a total loss.
The accident at Imperial Sugar was the deadliest industrial dust explosion in the United States in decades. It highlights the extremely serious nature of combustible dust hazards.
There were significant accumulations of sugar dust and spilled granulated sugar on surfaces throughout this facility. Conditions were set for a catastrophic accident.
Imperial Sugar's sprawling Port Wentworth complex began operations in 1917 and grew to become one of the largest sugar refining and packaging facilities in the U.S. Granulated sugar from the refinery was stored in 3 100-foot-tall silos and then conveyed into packing buildings where it was packaged for distribution. Granulated sugar was also converted into specialty products, such as brown sugar and powdered sugar. Sugar was transported by a complex system of bucket elevators, screw conveyors, and conveyor belts. During this process, sugar spilled onto floors throughout the work area. In places, the spilled sugar was many inches deep. This sugar also contained fine particles which became airborne. In addition, hammer mills were used to crush the granulated sugar into powdered sugar, creating even more dust. The machines were connected to a dust collection system, but it was undersized and in disrepair. And it was not connected to the bucket elevators and conveyors. Significant amounts of sugar dust escaped into the work areas. Workers routinely used compressed air to clean packaging machines, further dispersing sugar dust throughout the buildings. Over time, large amounts of dust accumulated on elevated, hard-to-clean surfaces, such as ducts, beams, and light fixtures. These surfaces were not cleaned often enough to always keep the dust below hazardous levels. In the tunnel beneath the sugar silos, granulated sugar flowed through chutes onto a long steel conveyor belt. From time to time, clumps of sugar would become stuck in one of the chutes, blocking the flow of sugar on the belt, spilling sugar onto the floor and releasing dust into the tunnel. But the tunnel was large and ventilated, so this airborne dust did not build up to explosive concentrations. However, in 2007, the company enclosed the conveyor belt with stainless steel panels to protect the sugar from possible contamination. The enclosure was not equipped with a dust collection system. As a consequence, sugar dust would now be trapped inside this enclosure. On February 7, 2008, clumps of sugar were found blocking one of the discharge chutes. Sugar from the adjacent silo likely spilled off the moving belt. Dust likely accumulated to an explosive concentration inside the enclosure. At about 7:15 p.m., the sugar dust contacted a nearby ignition source, likely an overheated bearing, and exploded. This primary explosion blew apart the enclosure and vented into the packing building. Accumulated sugar was lofted and ignited by the advancing fireballs. The dust clouds fueled a chain reaction of secondary explosions, which swept through the buildings. Concrete floors buckled, releasing tons of granulated and powdered sugar into the flames. Emergency evacuation drills had not been conducted, and the explosions had cut the power to much of the interior lighting. In the maze of darkened and damaged stairwells and passageways, workers desperately tried to flee the growing inferno. The CSB found that correspondence dating back to the late 1950s showed that plant managers in Port Wentworth were aware of the explosive nature of sugar dust and the danger of dust accumulations. As far back as 1961, a memo described a sugar dust explosion that heavily damaged the powdered sugar mill room.
Despite the long-standing awareness of the explosive nature of sugar dust, not enough was done to manage the hazard.
In 2006, the CSB issued a study of combustible dust, which called on OSHA to establish a comprehensive combustible dust standard based on the current standards of the National Fire Protection Association, or NFPA. In October 2007, OSHA began implementing a new national emphasis program to increase the enforcement of existing regulations related to combustible dust.
Imperial Sugar learned of the OSHA Combustible Dust National Emphasis Program 4 months before the devastating explosion at Port Wentworth. But management did not act effectively to control the serious dust problem in the packing buildings.
Less than 2 months before the disaster, an internal inspection showed that many tons of sugar were still regularly spilling onto the floors. This provided much of the fuel for the massive secondary explosions and fires. The CSB found that over the years, the Port Wentworth facility periodically experienced small fires fueled by spilled sugar and accumulated dust on equipment. But none resulted in a sugar dust explosion that propagated through the plant. Investigators said that decades of operating without a catastrophic explosion may have lulled managers into complacency. In its report, the CSB issued the following recommendations to the Imperial Sugar Company. Apply NFPA standards to the design and operation of the rebuilt Port Wentworth facility. Develop and implement comprehensive combustible dust control, housekeeping, and training programs. Improve emergency evacuation policies and procedures.
Companies can go a long way to control combustible dust within their own facilities by following the existing recommendations of the National Fire Protection Association. But it is also time for a comprehensive federal standard on combustible dust.
In April 2009, OSHA announced plans to begin rulemaking on a combustible dust standard for general industry. In its final report on the Imperial Sugar accident, the CSB recommended that OSHA move forward expeditiously with the new standard.
Without regulation, enforcement, and education, workers will continue to be at risk from catastrophic dust explosions.
For further information, please visit csb.gov.
Deflagration is a chemical process where a substance rapidly and intensely burns. This process is generally faster than combustion, but slightly slower than detonation. A good example here is of this deflagration is adding water to a burning oil that can cause deflagrations. The water rapidly boils to create steam and force the oil droplets to be ejected into the flame, adding fuel to the fire. After the next slides, I can show you a video of how a deflagration happens by pouring water onto a burning oil. Detonations, by the way, is a short wave that driven reactions at a velocity greater than the speed of sound in the medium.
Of all of the chemical compounds, and there are many millions, I think water has to be one of the most amazing, and it's one of my favourites. What we're going to do today is see how just a tiny amount of water can cause an enormous fireball.
This is a giant safety screen. It's going to be a giant cylindrical safety screen, as it will be, to protect Peter from the effects of pouring a small amount of water into some burning, boiling oil, which hopefully will produce a giant fireball, which, thanks to the screen, will go up rather than out. So we're going to take it up to the roof because no ordinary room could contain the fireball that we're hoping to produce.
As you may know, oil and water just don't mix. And I can show this. So we'll put some water in here and put some oil in here. The oil molecules are really actually quite large. They contain a lot of hydrogen, a lot of carbon atoms, a bit of oxygen, and maybe a few other elements, but this is really quite a large molecule. The water, just 3 atoms. Which one's going to come out on top? The amazing thing is the water is actually more dense than the oil, and this again is because of the interactions between the water molecules really holding them in closely together. The oil molecules are not polarized in the same way. They don't have that same separation of charge that the water does, and that's why we've got these separate layers. But what would happen if the oil was really hot? Here we've got around 100 millilitres of oil. We're going to heat this up and eventually it will catch fire. Then we're going to add some water to the burning oil. Now we've seen that the water sinks underneath the oil, and at this high temperature it's going to instantly turn into steam. And then we'll see what happens. 1 millilitre of water will produce enough steam to fill this entire flask, which takes up around 2,000 times the volume that the water did. Okay, I think we've got ignition here. We can have the gas off. Gas off. Okay, ready?
Yeah.
Well, now you can see why you should never add water to burning oil. How did it look? Did it come out the top or?
Really good. Yes, it did.
I did.
Several people.
What was it? So I have no idea, absolutely no, but I did feel this. It was good. Yeah.